Welcome to Cognitia, where we explore the deepest ideas about our universe and our place within it. Right now, we may be witnessing one of the most important turning points in modern cosmology. For decades, scientists believed we had a beautifully consistent model of the universe. It explained how everything began with the Big Bang, how matter formed, how galaxies assembled, and how space itself expands. This model, often called the Lambda-CDM model, matched observations with stunning precision. It was elegant, predictive, powerful. It felt complete. But in the last 15 years, something strange has been happening. The universe has started to misbehave, and not in small ways. Throughout history, moments like this have changed everything. In the 1800s, Uranus didn't move as predicted. Scientists calculated that another planet must be tugging on it. And Neptune was discovered exactly where mathematics predicted. But when Mercury's orbit refused to cooperate, no hidden planet fixed it. Instead, Einstein had to rewrite gravity itself. So today, we face a similar question. Are we missing something within our current model? Or is the model itself incomplete? First crack: cosmic structures too big to exist over the past decade. Astronomers have discovered enormous cosmic structures that stretch across billions of light-years. A giant arc spanning 3 billion light-years. A quasar group over 4 billion light-years wide. A galactic ring 5 billion light-years across. And a colossal Great Wall stretching nearly 10 billion light-years, roughly 10% of the observable universe. According to our best cosmological theory, this shouldn't happen. The universe is supposed to become uniform on very large scales. Beyond about 1 billion light-years, matter should smooth out like a blended soup. This idea, the cosmological principle, is foundational. It assumes that no region of the universe is special, and that what we see locally represents the whole. But these megastructures suggest otherwise. Even more unsettling, some surveys suggest we may live inside a massive local void. A cosmic desert about 2 billion light-years wide with fewer galaxies than expected. If true, that means our cosmic neighborhood might be unusual. And if we live in an unusual region, many of our measurements could be biased. Second crack: the universe expands at two different speeds. We know the universe is expanding. Since Edwin Hubble's discovery in 1929, we've measured this expansion rate, known as the Hubble constant, in multiple ways. One method looks at the early universe, studying the cosmic microwave background, the afterglow of the Big Bang. Another measures nearby exploding stars and galaxies in the present-day universe. Both methods are precise. Both are carefully tested. But they don't agree. One gives a value around 67 kilometers per second per megaparsec. The other gives about 73. That difference may sound small, but in cosmology, it's enormous. The statistical odds of this being random error are now less than 1 in a million. This tension has only grown stronger as measurements improve. If the expansion rate truly differs depending on how we measure it, something fundamental may be missing. Perhaps new physics, new particles, or new dynamics in dark energy. Third, crack: galaxies that grew up too fast. Then came the James Webb Space Telescope in 2021, designed to peer deeper into the past than ever before. It acts like a time machine. Because light takes time to travel, when we look billions of light-years away, we see galaxies as they were billions of years ago. Webb immediately found something shocking. Massive, bright, mature galaxies appearing just 280 million years after the Big Bang. According to our models, galaxies that large should not have formed until at least 500 million years after the Big Bang. Even more puzzling, some of these early galaxies contain heavy elements like carbon and oxygen. These elements can only form inside stars and are released when stars explode. That means entire generations of stars must have already formed, lived, and died extremely quickly. It's like finding skyscrapers in a prehistoric village. Either galaxy formation was dramatically faster than we thought, or our understanding of the early universe is incomplete. Additional cracks in the foundation, there are more problems. Our theory predicts 3 times more lithium than we observe in ancient stars, a discrepancy that has persisted for decades. Dark matter simulations predict steep density spikes at galaxy centers, yet we observe smoother distributions. Dark energy, once assumed constant, may actually be evolving over time, according to recent large-scale surveys. Even the interpretation of the cosmic microwave background, once considered settled, is now being revisited. None of these issues alone destroys the model, but together, they create pressure. From cracks to possible revolution, science advances through tension. When experiments consistently disagree with theory, one of 2 things happens. Either the theory adapts and becomes more refined, or it breaks and something deeper replaces it. We don't yet know whether we're in a Neptune moment where hidden ingredients like new particles or subtle corrections will fix everything, or a Mercury moment where a radical shift in understanding is required. But we do know this. For the first time in decades, cosmology feels uncertain. And uncertainty is where revolutions are born. The universe is telling us that our story is unfinished. And that is incredibly exciting, because it means we are not at the end of discovery. We are at the edge of something bigger. Thank you for watching Cognitia. If you're fascinated by the mysteries of the cosmos and the ideas that challenge everything we think we know, subscribe and join us. Because here at Cognitia, we don't just learn about the universe, we question it. And the next breakthrough might change everything. See you in the next exploration.